Okay, this is the formula that we just derived. Now the question is, how do I find these orthonormal vectors u and v? Because if I have these and I have my matrix A, I can calculate my singular values. So the first thing that we're gonna do is we're gonna calculate A transpose A. A transpose A means, so I transpose this one, use sigma V transpose. This is A transpose times A is again U sigma V transpose. Okay. Now remember that A times B transpose equals B transpose A transpose. We've seen this before. In order to calculate this, you need to swap the order. So we're gonna do this here. So V transpose transpose becomes V. Then this becomes sigma transpose and U transpose. Okay? So we have U here, then again sigma V transpose. Now this here is of course the identity matrix. So now if we're gonna do A transpose A, and we're gonna multiply this with V, then we can do the same here. Then it is V, and then this is sigma squared, right? This times this sigma squared, and then we have V transpose V. So this is again, we can drop this, so we have A transpose A working on a vector V equals sigma square working on a vector V. And what do we see here? We see here that that A transport that V is actually an eigenvector of A transpose A. Remember, eigenvector A working on a vector equals lambda that vector. So an eigenvector is unaffected by a matrix transformation. We've seen that in linear algebra. So here you can exactly see that we have that number. So from this we can calculate V. Okay? V is just an eigenvector of A transpose A. Okay? Then the next thing we're gonna do is we're gonna calculate A transpose. So that means U sigma V transpose, and that times U sigma V transpose transpose. Okay? So we calculate this is U sigma V transpose, and then we have V sigma transpose U transpose. Okay, this is here again the identity matrix, like here. So that means that this is U sigma squared U sigma squared U transpose. So if we now do A times A transpose times U, then we have U sigma squared, and then U transpose times U is the identity. So here we have A transpose working on a vector U equals sigma squared U. So from this we can calculate U. Because again, U is an eigenvector of A transpose. Okay? So this will allow us to calculate the sigmas. And of course, how can we retain as much of the variance as possible? So retain variance. very similar to what we had with the PCA. So you have sigma 1, sigma 2, and so on to sigma k, and we divide it by sigma 1 to sigma 2 by sigma n. Yeah? And you want this to be 99%, for example, if you want to retain 99% of the value. Okay, that was it for the optional refresher on PCA and SVD. Thank you. See you next time. Okay, so now how are we going to do the dimensionality reduction? Well, sigma squared, what is that? Well, it's sigma 1 squared all the way down to sigma n squared in n dimensions. Yeah. So basically, if we want to keep k significant values, singular values, basically what we're going to do is sigma 1 squared, sigma 2 squared, all the way down to sigma k squared, and that divide by sigma 1 squared, comma, all the way to sigma n squared. Yeah? And k is of course much smaller than n. And this we wanna keep as high as possible. We want to retain as much variance as possible. So we want to keep this, 99%, 95%. Okay, that was it for dimensionality reduction. What we're gonna do is I'm gonna apply PCA on the Pima Indian case that we have used for k-nearest neighbors. I doubt that it will have effect because we're not in high dimensions. We only had 8 features. Yeah. So PCA might not give you a better result. So the only thing I want to do is to show you the few lines of codes it takes to implement PCA. Yeah? So that, whenever we need it later, we can apply it. Okay, thank you. See you next time.